Welcome, everyone. Thank you for being here today. Shantae, if you'd like to take it away.
Well, good afternoon, everyone. Welcome and thank you for joining us for today's webinar. Today's webinar titled Equitable Placement and Completion AB 1705, Innovative Course Curriculum. Our spotlight today is on Santa Monica College. We're grateful for our featured presenters that are joining us today. Today's webinar is also hosted by the California Community College's Chancellor's Office, Education Services and Support Division, in partnership with the RP Group. Just want to welcome today's presenters as well. Again, our featured Spotlight College is Santa Monica College. So a warm welcome. First, we have Adam Richardson, an innovative course instructor with Santa Monica College. Joining Adam, we also have Brian Rodas, innovative course instructor as well from Santa Monica College. Again, welcome. Thank you so much, professors, for your featured expertise in today's webinar. And without further ado, I will turn it over to you. So again, welcome and thank you.
Thank you. Thank you. Well, good afternoon, everyone, and welcome to our webinar, Equitable Placement and Completion, AB 1705, an innovative course curriculum here at Santa Monica College. My name is Brian Rodas, and I am the Assistant Chair of the Mathematics Department here at Santa Monica College. I'm really excited to be here with Dr. Adam Richardson, faculty in our math department. And we're both really excited to share with you a wonderful course that we intend to start offering starting this fall. As you all know, the Chancellor's Office sent a memo in February of 2024 saying that all colleges needed to submit an AB 1705 STEM Calculus Pathway Certification form last July, stating their compliance status and plans. And you may recall also that the memo listed 4 options for colleges to choose from. We elected to go with option D, which was to create and implement an innovative preparatory course of no more than 4 units with no more than 2 units of concurrent support. So we would like to present to you this innovative course that we've created. And I'd like to now turn this over to Adam to tell you all about it. Adam?
Great. Thank you, Brian. Thank you so much. And thank you to the Chancellor's Office and the RP Group for giving us this opportunity. I am super excited to share all this stuff. So I'm going to go ahead and get started. One thing I'll say is we only have an hour, so I did have to cut a lot of things. However, I'm more than happy to stay after and answer further questions, maybe show some additional resources if anybody is interested. What I'm going to do here is I'm going to start by sharing the slides. There we go. And then I'm also going to post these documents in the chat. 1 second here. Sorry about that. I'm going to post these in the chat right now so that you can download and follow along if you'd like. Okay, looks like it went through. Okay, all right. So let me go ahead and get started. There we go. Okay, so just a quick overview of what I'm going to go through. I'm going to take a look at the general course info, which is one of the handouts that I posted in the chat. Then we're going to take a look at the Math 6 plus 6C table of contents. Then I want to talk about some pedagogical motivations, just some pedagogical reasons for choices we made when developing this course. And then I want to spend the rest of the time looking at some content snapshots. That's what I had to pare down quite a lot. So if you're interested in seeing more or asking questions more after the 1 hour is over, I can stay and answer some more. Then I have some acknowledgments because we had a lot of help with the development of this course. And then I'll open up the floor for Q&A. All right, so first I'm just going to pull up this handout with just general course info, and I'm going to move through it a little bit quickly right here. So first I'll just say this. The course is Math 6 plus 6C, and it's titled Modern Mathematical Methods for STEM Majors. The total unit count for 6 plus 6C is the co-requisite part, is 4 units total. But that amounts to 6 hours in class. So we have lecture and lab parity here at SMC. Students that are enrolled in Math 6 must also be enrolled in the co-requisite part, Math 6C. Here's the catalog description. You're welcome to read that at your leisure, but I kind of want to skip down to this part because this is the question that everybody asks me when I'm walking down the hall and has been asking me for about a year now. So what makes Math 6 plus 6C innovative? For one, it's only 4 units. It is the TC. Some of the content in the course is emphasized based on collaboration with the other STEM departments. So we reached out and talked to other STEM departments about what they think their students would need when they enter their courses. We've also looped in a bunch of students to help develop this course, in particular Derivita, which is the homework platform we're using for this course. The course is designed with a flipped format in mind. We're also going to be emphasizing active learning and in particular content delivery through active learning. So what I mean is the active learning is not just a review of what students have already seen in the lecture, for example. We are also going to be incorporating the use of physical manipulatives in this course. We are going to have embedded tutors in every section, and we are pretty sure we're going to have embedded counselors in every section. We'll see. We're supposed to, we think we will, but we're not totally sure. There's also going to be an emphasis on modern mathematical approaches and concerns. I'll show you some examples of that as we go on. There's also an emphasis on mathematical intuition, which I'll talk a little bit more about later. One of the things that's really cool about this course is that it ties together basic math and advanced math. And we also continually link algebra and geometry. So for example, if we get a solution by solving some equation algebraically, we will take a look at what that looks like geometrically as well. There's like a link between algebra and geometry. We also are incorporating modern mathematical technology, in particular Mathematica and then Desmos. Every student at SMC and faculty, I should say, everyone at SMC has free access to Mathematica. We secured funding for that. And they also have access to Wolfram Alpha Pro. So in this course, we give students a little bit of a taste of using that mathematical software. We also emphasize answering big questions. For example, when will I use this in my STEM career? Like, when will I use this in life? That gets answered continually through the course. And there's also an acknowledgement of the mathematical horizon. So what, what can students expect to see far beyond in their mathematical journey? So some student resources, I'm going to kind of fly through this, so I do apologize. The course is ZTC. All the resources have been developed and created and curated by the Math 6 development team here at SMC, and it'll be offered free to the students. We secured funding from a combo of sources to make this possible. There's no textbook, but there's a variety of other resources that students will get. So students will have free access to a set of slides, a pre-recorded lecture, associated fill-in notes that mirror the slides in the lecture, in-class activities associated with each section, and solutions to those activities made available the next day. And then there's an online derivative homework set for each one of these sections as well. Like I mentioned before, students will also have access to an embedded tutor, hopefully an embedded counselor. We also developed a generic weekly schedule spreadsheet just to help students schedule their weekly lives, you could say. It's something that students really need help with actually budgeting their time. So it's a good skill to go over. We also have a handout on breathing exercises to help mitigate testing anxiety. And that was developed by our SMC dance department chair, Mark Tomasic. And so for instructors, there is also a 73-page complete instructor's manual to address pedagogical questions. So if an instructor has not taught the course yet, the manual basically says, okay, here's what we're covering in these sections, or we'll say this section. Here's a bullet point of why certain decisions were made, things that you can emphasize, things that you could de-emphasize if you need to. And it covers both the lecture and the activity that's associated with it. So that's just a general course info. So you're welcome to skim over that more at your leisure. The next thing I want to do is take a look at the table of contents. So let me switch to that. Give me 1 second. There we go. And again, I'm just going to kind of skim it, and we're going to focus on a couple of particular sections. So there's an introductory section, which is just kind of an intro to the course. Chapter 1 is a foundations chapter, and that chapter is basically priming students to use fundamental ideas later on in the course. Today, we're actually going to focus on 1.1, fundamental intuition, 1.4, the theory of approximation, and then we'll see how that ties in when we get down here to 3.5. There's a chapter on functions. A lot of that is standard pre-calculus fare that you've seen in a regular pre-calculus class. Some of the ways things have been introduced is slightly different. Chapter 3 is on polynomials and rational functions, and there are some unique choices that we've made for this chapter. So for example, we discuss polynomials and the Weierstrass approximation theorem. This has to do with answering those big questions like when will I use this in my STEM career? There is a whole section on factoring quadratic polynomials, but again, the question is kind of like why? Why do we emphasize factoring quadratics? Why do we spend so much time on it? Well, if you're aware of the Weierstrass approximation theorem and the fundamental theorem of algebra, those kind of tie together to motivate the study of polynomials. So we have that included there. Another thing that we do is we break the topic of rational functions into two sections. One section is just local behavior of rational functions. So you can think like intercepts, vertical asymptotes, that kind of stuff, turning points. And then the second part is asymptotic behavior and graphs of rational functions. So we're looking at a global picture of those things like end behavior and so on, and asymptotic analysis. Chapter 4 is usual, standard fare, exponential functions, logs, properties of logs. Chapter 5 is also pretty standard, sequences, summations, the binomial theorem. What is unique about this particular chapter is 5.2, where we will talk about comparing asymptotic behavior. We actually introduce big O notation in this section, just to get students thinking about how functions grow at different rates. Chapter 6 is the chapter on trigonometry. And then there's a supplementary section or supplementary chapter, which has two sections. One is more about conic sections. You might notice that conic sections are not explicitly listed in this table of contents. They're covered through those sections. So they appear, but they're covered throughout those sections. And then the law of sines to round everything out. Next I want to talk about some pedagogical motivations. So let me share my screen. Ooh, where did it go? Right here. All right. Oop, there we go. Okay, so yeah, so there have been a lot of structural decisions made when we developed this course based on pedagogical things. So in particular, the flipped format, active learning and the use of physical manipulatives, specific content, what to cover and what not to cover. We'll talk a little bit about remediation, collaboration with other departments. We'll talk about Derivita, the online homework system that we went with for this course, collaboration and cooperation with students, the course schedule, and then again, embedded tutors and embedded counselors. So one thing is we wanted to make this course flipped. So students watch high quality pre-recorded lectures. And then when they come to class, that time is spent primarily for active learning. So we're going for about a 30-70 split. The way that I run things is when students come in, I can answer questions, I can emphasize certain things from the lecture, but that's not supposed to be the whole time. Really, most of the time is spent doing active learning, working on an activity and working with groups, getting our hands dirty. We actually have 360-degree whiteboards now in our new building, so we'll be using those. So your hands really will get dirty. One thing is all class sections for at least the first year are going to be on ground and in person. We would like to extend this to an online course, but we are going to see how things go in person at least the first year. One thing about the benefit of a flipped format is that you never really fall behind, which is really common if you're doing a synchronous lecture. And if you feel the need to go back to a lecture format, you can if you've already flipped your course. So that's one of the benefits about flipping a course. Active learning. So yeah, active learning is going to be emphasized, and we have pulled out all the stops with this course. I already mentioned the whiteboards. Some of the activities will take place in a computer lab. Students will use Mathematica and Desmos just to get some experience with this modern mathematical software. We can also use Derivita spot checks in class. They're kind of like an iClicker poll, but the questions you can ask are way more robust, as you'll see when I get to that stuff. Physical manipulatives. So several of the activities actually involve the use of physical manipulatives, like Cuisenaire rods, if you've used those before, linking cubes, algebra tires, algebra tiles, and paper rulers. So for example, the paper rulers we're actually going to use to have students perform physical graphical arithmetic. So they can really see, what we mean when we talk about f of x plus g of x or f of x divided by g of x. So they're going to physically measure those quantities and work them out. Next, I want to talk a little bit about the content. So a lot of thought has gone into what to include and what not to include. So for those of you that are developing your own innovative course, this question can kind of help guide what you might want to include or not. So the question is, should this concept serve as a gatekeeping mechanism for the calculus sequence? So for your consideration, the law of sines, bounds on zeros of polynomials, induction, these are concepts that I would say should not serve as gatekeeping mechanisms for the calculus sequence. They are definitely they can precede calculus, that's for sure. But there are other topics, other concepts that I think students really need to know to do well in calculus. So compare those to, so for example, the difference quotient or just the concept of a function. That's like the biggest one. The graphs of the trigonometric functions, those students really need to be comfortable with those. And even, asymptotic behavior of rational functions, that kind of stuff. So there's an emphasis on mathematical intuition, making sense of things, making meaning of things. So a lot of times students that are exiting or are still in the K-12 system, a lot of times they lack mathematical intuition and they see math as a system of rules just to memorize and regurgitate. And we're trying to move them away from that interpretation of math. I actually really like this quote from Terrence Tao. He said, the main reason people think that they're bad at math or don't have the math gene is that mathematics is often taught in a very prescriptive manner, and it's not natural to think this way. Oftentimes, we have to learn all of these drills and rules, and it's not tied much to our intuition. There are different ways in which people can access math. Some people are very visual, some people are very logical, some people are very systematic, and they're all valid ways of approaching mathematics. So we really want to tie things into intuition, bringing that intuition forward in the course. I also recommend you check out this blog that he wrote called There's More to Math Than Rigor and Proofs. Students at the pre-calculus level are at the pre-rigorous stage, and the transition the transition to rigor occurs during and after the calculus sequence. That's when things start getting more rigorous. So keep that in mind. This course also emphasizes big picture ideas, and it has a succinct, consistent narrative throughout the course. I like to say that a math course is like a story. It's got a middle, an end, plot lines, recurring characters, cameos, etc. And this course seeks to tell a story that leaves the reader, in this case, the students, excited for the sequel, which is the calculus sequence. So we want them leaving the course really intrigued and interested in what's going to come next. So yeah, talk a little bit about remediation. So what we're proposing is not really remediation. It's drawing meaningful connections and analogies between basic math and advanced math that students can understand. It's like making these connecting threads. I've noticed in my classes, a lot of times students who are not considered, quote, behind still lack a fundamental intuition of math. They've gotten really good at manipulating equations and things, but they don't quite know what they're doing and they can't express things in an intuitive way. So they're missing kind of like half the picture. So we're going to draw explicit connections between basic and advanced math. One example I like to use is fractions. So pretty much every student struggles with fractions. But just because a student doesn't understand fractions, that doesn't necessarily mean they need to go back to intermediate algebra and take a whole course in intermediate algebra. What they really need is they need an explicit contemporaneous review of the intuition for fractions that's incorporated through that course, through their modern course. And Math 6+6C has this. A lot of times people wonder, how would we make time to rebuild this intuition to go over these concepts that students, quote, should already know? It's a flipped format. This was one of the biggest suggestions that Lisa Morales and Paula Young gave us when they were hosting those communities of practice related to developing a co-rec for Calc 1. And even other presenters at those conferences really were just like, you have to at least partially flip your class. So you have more time to talk about these things when you have a flipped format. There's also been interdepartmental collaboration when this course was developed. So I met with the department heads and asked them what skills they think their students need to know when they enter their science classes. And I recommend that you do that too if you're developing an innovative course. Their answers might surprise you. It may not be what you think students need to know leaving a math class. So I met with reps from chemistry, physics, computer science, and their input was invaluable. And I'm gonna have to pull out another quote from Terrence Tao here. He said, most students who take math classes aren't going to be mathematicians. They're going to be engineers, statisticians, other careers. So in many ways, that's the more important mission of math education. Yeah, I'm a mathematician. That's what I like to do, but I have to respect and understand that most of my students are not going to be mathematicians. But maybe if we emphasize intuition, we might convert some of them. So I've converted several to the field of math. Oh, other things. So we've actually included some specific concepts and problems that students will see in their major courses in Math 6+6C. So I know there's one question that students will see in chemistry that shows up in the section on logarithms. So there's other little like Easter eggs that students are going to see later on as well. And why is this important? It's because this helps drive STEM STEAM, right? We want to keep students interested. We don't want them to get into a math class and then bail, be like, oh man, I'm done with STEM. If this is STEM, I'm done with it. So meaningfulness, context, reason, and purpose beyond simply needing a skill for the next math class. This is a big thing. You can't motivate learning math by saying that you're going to need this for the next math class. You've got to reach beyond that. That's not enough to keep students interested, right? So insight from other departments can really help those of you who are developing your own innovative courses. Derivata. So I want to talk about Derivata for a minute here. Students really need to have an associated online homework platform so they can get on the spot feedback outside of the classroom. We looked at several different online homework platforms, but Derivata, hands down, was just the best choice for our use case for several reasons. It's just incredibly robust. So some reasons why we chose it. For one, it is not tied to any textbook. This is a standalone homework platform. It's device agnostic. So that means that it works on any device. So desktop, laptop, tablet, phone, smartphone, it works on any of those devices. What's really amazing is the types of questions that you can ask are just really robust and customizable. And I'll show you some examples in just a few minutes here. Yeah, the feedback is also fully customizable. So when a student enters an answer, if they enter it in a particular way, you can customize the feedback string that gets shown to them when they go to check their answer. Another thing that attracted me is the advanced question editor uses a programming language that is easy to learn and code in. So if you've ever tried to code your own web assigned problems, for example, or even problems on MyOpenMath, it can be difficult. And this language is much easier in my experience. If you're not into making your own problems, it already has a massive question bank. So you can just pick problems they already have. And again, you can also use spot check in class. Oh yeah, it also integrates seamlessly into all the learning management systems. Now, one thing is it's not free, but the cost is minimal. It's $35 a year. And that works perfectly for our students because students that'll be taking Math 6 plus 6C will likely be taking Math 7 plus 7C the following semester, and that's our Calculus 1 with co-requisite support. We actually secured funding for these resources, so students that are in these courses will not have to pay for any of this. If you're interested in learning more, you can contact Josh Dyer. He's our representative at Derivata. He's actually in attendance today as well. So if you have more questions about Derivata, he might be able to answer them as well. Student collaboration. So one of the amazing things about this course is I've been working with 4 student coders to create all of the homework problems for this course. And what they've been doing is just phenomenal. We got funding to hire them to help develop these homework problems, and they were able to learn the language literally in a month or so. And that I think some of them are actually in here right now, but we've been working together since August, and we're going to be working together at least through this semester and probably next semester. But they are able to code from scratch these homework problems that are just incredibly robust. They also provide a ton of insight into what students would want to hear when they are doing these problems, you know? So I remember Jack, one of the coders, mentioned I had a question where I wanted one of the zeros of a polynomial to be an imaginary number, but I didn't want to, oh no, I'm sorry, an irrational number, but I didn't want to include the conjugate. And the coefficients for the polynomial were just absolutely nasty. And he was like, I don't know if this is fair to ask a student to enter this. And I was like, yeah, you're right. Okay, we need to fix this. So their input has been invaluable, and their contributions have been just awesome. Wrapping up a little bit here, the way or the schedule of the content delivery has been carefully crafted, including like exam days and review days, partially to allow curricular flexibility, also to frankly not put all of the really hard stuff at the beginning and then at the end, because that's just when students just burn out when you do that. If you have really hard stuff at the beginning and then you save the really hard stuff for the end, we tried to avoid that. So things are turned a little bit to put the more difficult stuff at about the 70% mark. Also, because we have a flipped format and the way things are structured, at least with this round, we're going to be using exams as one of the main assessment methods. But if an instructor wanted to use presentations or projects, there is time allotted for that. So if they want to switch to something that involves more presentations or projects, they can. The time is built in there. And embedded tutors and counselors. I've kind of already talked about that, so I think I will skip that. All right, so now what I want to do is take a look at some content snapshots just to give you some quick looks at what the content looks like. The first one is just going to be section 0.0, the introduction. I'm just going to look at one slide. So this is day 1 of the course. And these are some of the big questions that I tell my students they need to be asking all the time, not even just my course, but every course, every day of their life. Why am I learning this? Why should I care about this? When will I use this in my STEM career? What is the intuition for this idea? Does this make sense? And when do I lose the feeling of understanding? Because I think anybody that teaches math or has taken math or learned math, you know there's a moment where you just completely lose your follow, you can't follow anymore, right? But as instructors, we don't know exactly when that happens. We can kind of go off of students' eyes and just kind of their facial expressions, but a lot of students don't realize that they should be keeping track of that and trying to ask themselves, wait, when does this suddenly, when do I get lost? And when they do that, they need to shoot their hand up and ask a question. So this is like a conversation you have literally on day one of the course, and then you reiterate it throughout the course. Next, I want to talk about Section 1.1. This is day 2 of the course, and this is all about fundamental intuition. So we're going very far back and trying to remind students or teach students basic intuition for the operations that they may have never seen or don't remember, right? So this is not the entire content section. This is just some of the slides that I pulled from it. So it's not the whole section. This is the overview for that particular content section. We discussed the difference between intuition and rigor with students just to help them understand that there's a difference. Yeah, mathematical intuition, it's critically important. It serves as a really helpful guide. It's a way for us to make sense of the ideas we're exploring, but it can't carry us the whole way to the truth. That's why we need rigor. This is a motivation for studying advanced math, right? Your intuition can carry you really far. What happens when you get to a point where your intuition fails? Math. That's what happens. Advanced math, rigorous math comes in to save you. Yeah, so rigor is necessary, but we need to talk about intuition too. I linked this blog. I think it's a really good blog post. Let's see, what do I want to focus on next? Oh, so here's an example. We talk about fundamental intuition of just the operations, addition, subtraction, multiplication, division, just to refresh their memories and teach them these things, right? Multiplication stretches or compresses quantities, gives them a physical way of thinking about it. Multiplication can always be represented as an area. This becomes really important when you start exploring things like the mechanics of the Riemann integral, right? F of x times delta x is an area, it's a product. Exponentiation, just getting them thinking about when whole numbers are involved, you can think about an exponent as telling you to multiply a certain number of times. And then fractions. So there's a significant amount of time spent to trying to get students to have an intuitive understanding of fractions. This is a good way to start. So this symbol means how many times does B fit inside of A, or how much of B fits inside A. And that's what that number represents. So it sounds basic, but I swear, just going over this little basic thing and reiterating it throughout the course, it just opens their minds and opens their worlds. It's really cool. So this is a good example. 3/2. Well, that means how many times does 2 fit inside of 3? It fits in there one whole time and then half of another time. That's why it's 1.5. 3/2 is 1.5. Here's an example where we're using strip diagrams, and then in the activity, students will actually use Cuisenaire rods to do this kind of a modeling. Again, this is day 1, so they can really get a physical idea of what's going on. Oh yeah, this is also what's nice about that. When you start to bring in these intuitive ideas for fractions, these types of questions or these types of inequalities become very clear. If B is smaller than A, then A over B has to be greater than 1 because B can fit into A at least once. So you can fit B into A more than one time, right? If B is greater than A, then A over B is less than 1. They can't fit, you can't even fit B in there even one time, so it's got to be less than 1. And if they're equal, it can fit in there exactly one time, and that's why, when you divide a number by itself, you get 1, other than 0, right? Right. Now, this is actually one of my favorite activities or favorite examples to show, and this again is day 2 of the course. Now let's take things up a notch, right? So suppose x is greater than 0. How many times does x fit into 1? Or in other words, what is 1 over x? And then you can kind of ask the students this, and as x gets very large, it can't fit into 1 as many times. So the number of times it can fit in goes down. If x is equal to 1, it's 1. And if x gets really small in size, you can start to fit that number into 1 more and more and more. So the number of times increases. And lo and behold, you just reproduce the graph of 1 over x. at least the positive part of it, right? So, oh, of course, so that we can preview the program. Oh yeah, I'm going to share some derivative examples right now. Yeah, right now. I just wanted to get through this bit right here. Yeah, perfect timing. So this is a really good example to show students. But now let me let me let me do this. Okay, I'll do this. Since somebody was asking about derivative, let me share one of the questions from that section. I'll do this right here. Okay, so I have a bunch of derivative questions. This is what it looks like in the back end, I'll say, but this is one of the questions that we're asking the students on their online homework. So let me preview it. Here we go. It says use this Desmos widget below to model the product 10 times 4 as an area. And then what students can do is they can move this, right? And they can try to set it up. Let's see, 10 times 4. There we go, 10 by 4, and they can check their answer. Correct, good job. So what I'm saying is this was totally coded by myself and the student coders. This feedback you're seeing, we choose that. We can choose what it says. If you want to see what it looks like on a phone, this is what it would look like if a student was doing it on their phone. Let's say they get it wrong. So let's do this maybe, right? Okay, now check the answer. It'll throw them a feedback string that says, wait, something's not right. You have full control over this. You can have it say whatever you want it to say. What are the factors in this product? Each factor can be represented by the side of a rectangle with that length. Maybe now they can try it again and see if they get it right as many times as they want. Solutions. So there's a solution that'll pop up once they get it right. And again, you have full control over the solutions, what it says, how it says it. By the way, this is all fully randomized. So you notice that this was 10 times 4. That's random. You can choose the extent of the randomization. It's not always going to be 10 times 4. It'll be 1 times 3, 2 times 8, any of that stuff. And then solutions that reflect that. So that's just one example, right? One example. Okay, now what I want to do. Okay, let me go to the next section here. Let me go to this. Okay. Yeah, oops, there we go. So theory of approximation. One of the things that we emphasize in this course is just the theory of approximation, because a lot of times students don't realize there's a difference between an approximation and an exact value or an equality. So we talk about it, and we talk about the notion of an error and how important this notion of errors and approximations is later on. So we also just kind of touch on the idea of machine learning. So one of the main things you study in calculus is how good an approximation is. And limits are essentially approximations that are getting closer and closer to an exact value, right? And if that limit exists, they converge to that exact value. So we talk about how machine learning and large language models are universal approximators. They're approximating things and spitting out what they think you want to hear. Um, so there's an approximation that's correct to some degree of accuracy, but there's an error associated with any approximation. This gets us talking about the distance between these approximations and these exact values. So we talk about absolute value, but first, approximations are not equalities. Talk about not abusing the equal sign. This is a classic one. Like a lot of students think 1/3 is 0.33. And we explain to them that's not 0.33, but it is close. It's approximately 0.33. That's the hand wave, right? So we explicitly discuss this in this course. And then we introduce them to this particular symbol. I'm not sure how many of you have encountered this, but I was pretty surprised when I was teaching calculus the second time. Oops. Most of my students had not seen this expression or realized that this was the distance between two numbers. They did see it a long time ago, but they certainly didn't remember it, and they certainly didn't have any intuition for it. But this is critical if you want to understand things like the formal definition of a limit or just the notion of an approximation, right? So we review it, we talk about this idea, and we're just using intuition to solve these problems. One of the things about the first chapter is there's really not a lot of algebra. It's more number sense, problem solving, using intuition to solve these types of problems, not so much solving for X. And you can talk about stuff like this. So the difference between the whole part of a rational number and the whole part plus its fractional part is going to be the fractional part. This is actually going to lead us into stuff about rational functions later on. This type of thing. For what numbers x does x minus 4 equal 9? You don't need algebra to solve this. You just need to understand that this means the distance between x and 4 is 9. So what numbers are 9 away from 4? Boom, there you go. So this is reiterated on the activity, for example, which I can show you. And then we can also throw in the algebraic solution, right? Use the definition of absolute value, run through the two different solutions. So there's an algebraic result too. So tying intuition into algebra and geometry, all connecting. Then we talk about errors. So hopefully this expression or this inequality looks familiar to you all, right? Because students struggle with it a lot. We hit them with it in chapter 1. Let's start making sense of what this means and let's build some intuition for it. We talk about epsilon as being an error or a tolerance. I used to work in industry and we would always be given a tolerance whenever we had to build something, right? So there's an exact value that you're trying to get, L, and then there's a tolerance you're given, and whatever approximation you get has to be within that tolerance. That's the idea. So we introduced them to this concept in Math 6 plus 6C. Here's just the expanding this, right, as a compound inequality. Here's a visualization of what that means. So they can associate this inequality with this picture, right? And then we can talk about that as an interval. And then here's an application problem, something similar to what I've had to do before when I was working in industry, right? You've been contracted to make a box that has an internal width of 13.2 centimeters. The tolerance is 1 millimeter. What's the smallest the interior width of the box can be? What's the largest? And then they set up this inequality. And then again, there's really not much algebra going on here. It's really just making sense of what this inequality is saying. So that, oh yeah, there we go. And then here's a picture of the solution set, right? Let me show you an example of this on Derivata now. So, oops, sorry. Here we go. So I have a couple, there's my mouse, a couple of these. So this is a general version, and this is a version with a number that is randomized, right? So let me preview this. So let L be an exact value. Y is an approximation of L. Oh yeah, the letters are randomizable too, by the way. That's why it says Y instead of X. It depends on the randomization. So they have to write an absolute value inequality. They can use the word error for epsilon. So let's see. X minus L is less than 2. Let's say that's it, right? They can check their answer. Oop. So for one, Derivata actually renders their input live so they can see what they're putting in. And it says, oop, looks like you're using the wrong symbol for the approximate value. Oh, yeah, it was Y, right? Not X. My bad. There we go. Let's try that again. Not quite. Remember, the distance is this. Oh, I should be using error. So not 2, right? All that feedback you're reading is written by myself and the student coders. Like we get to choose all that stuff. There we go. Got it. Got it. Now rewrite this answer as a compound inequality in terms of Y minus L. So minus L, error. Okay, let's check that. There we go. And so on, right? So it's kind of scaffolding that this particular symbol and then how you can write it as an interval. So it kind of goes along with the example that you were just seeing, just like that. Oh, again, and you can also, this is what it looks like on a phone. So if a student's using a phone, that's what it looks like. Let's see. This one is basically the same, so I'll skip that. But this is one question I'd like to show you all. See, I'm getting a little bit low on time. Okay, let me show you this at least. All right, so this is a question where I'm asking the students to mark an approximation of pi on the number line. Here's pi, and this is the approximation I want them to mark. And so they can move this. They have control over this, right? They're gonna have to zoom in a little bit here. Get closer, closer, closer. Maybe I think that's right. Let's check the answer. You're close. Make sure you're placing the point right at that value right there. Okay, let me try again, and they can keep going. One of the nice things about Derivata is it has an interactive Desmos interface, which means you can send information into these Desmos widgets and get information out, and it's auto-graded. So this is a cool example. Again, this is what it looks like on the phone. Oh, forgot to resize that. There you go. I have another one where they do the square root of 2, and this one I have modeled as, oops, sorry, preview. This one I actually have modeled as the diagonal of a square. So it's the same kind of thing. They just have to get right to that approximation of square root of 2. So it's another cool example. Okay, now the next thing I wanted to show was something from section 3.5, and then probably take a few more minutes and then we can open the floor for questions. Here we go. Okay, polynomials and the Weierstrass approximation theorem. This is the overview for that section. We do talk about limits and we talk about the limit operator in this class. I'll get to that in a minute. Basic definition of polynomials, some easy pictures of what's a polynomial and what's not a polynomial, and then this theorem. So this theorem is actually critically important and it gets used a lot in applications. It basically says if you've got a continuous function on a closed interval, then you can approximate it arbitrarily closely with a polynomial. So a lot of times what people will do in application, if they're dealing with a really pathological function, like a gross function, they'll just pass to a polynomial that's pretty close. but they accept a little bit of error with that approximation, right? So that's the idea here. And you'll notice that now through these sections, the interpretation of this symbol and just understanding this idea has been well scaffolded since the first chapter, right? Knowing what that symbol means, knowing about the number line, knowing what this inequality is, it's been set up so when they get to this, they can really see how we're using it in a modern mathematical way, like that concerns modern mathematical applications. Um, yeah, exactly. So in essence, we could use a much nicer type of function in our analysis in place of what might be a highly pathological function if we're okay with a small error. What's funny is this is exactly what students do in Calc 2. So if you've ever taught Calc 2 and you talk about Taylor series, you are computing literal polynomial approximations to functions like sine, cosine, and so on, right? That's what they're doing. They're computing a polynomial that approximates this function to a certain degree of accuracy, and there's an error associated with that approximation. So this is a ninth order approximation. Physicists in the audience, a lot of times physicists will just approximate sine of x, as long as x is very small, very near zero. They'll just not bother with dealing with sine of x. They'll just use x instead, right? It's not exact, it's an approximation. And actually, I'll show you that Desmos activity too in a minute. We do talk about the limit operator, and we talk to them about using it as essentially a function that tells you where things or values are going as x approaches some value. So the limit operator is introduced in this course, but we do not do the algebra of limits. So we're not doing things like limit of f of x plus limit of g of x, that type of stuff. We're just talking about what this thing actually does, what the limit operator does itself. Some basic pictures here. Let me show you some examples. Okay, let me do this. Perfect. Okay. Boo. All right, so this is the activity associated with that section, 3.5. And here they're exploring the Weierstrass approximation theorem. Here's cosine x. Here's an approximation. Here's another approximation. Here's another approximation, another one. And again, where these are coming from, students won't see this until Calc 2, but they're getting a taste of it now, and they're understanding that these polynomials are approximating this function, this cosine function, right? And then here are the actual numerical values, the numerical approximations. Let me show you where is it? Yeah, let me show you this as well. Let me show you the handout for that activity right here. Yeah, it's right here. Here we go. So Desmos exploration. They do a bit of graphical arithmetic first using the physical graphs. And then here's the activity I was just showing you. What I was showing you is actually the solution to this activity. So students would construct all of this on their own on Desmos, but that's what it is, right? What do you notice about the graphs of those polynomials and the graph of cosine? Which polynomials above satisfy this condition? Scientific notation is also discussed in this course in chapter 1, section 1.3, I believe. Yeah, so that's the Desmos part of the activity. And then some standard fare questions about construct a polynomial that has zeros at these points and so on and so on. Yeah, well, okay. So let me show you one last Desmos example. I'm sorry, a derivative example, and then I'll kind of wrap things up. Like I said, I could go on for many hours with all the things that I was excited to show you, so I'll just have to wrap it up real quick here. Check out this question. So this is a question that was specified by Jason Wang, one of the people on the Math 6 development team, because he really likes transformations of functions and graphs, right? So here we give a student a graph, and we want them to graph this transformation by moving the points below. So they can grab these, they can move them around and things like that. And the way that I coded this, I wanted to give them more granular feedback, like if it's wrong, right? I don't want them to have to fish around for what's wrong as much. So let's check it. So here, I actually coded it so that it will tell you what coordinates are not correct. So it's like, oh, it looks like the x coordinate of this is incorrect. Remember, when the input of a function is transformed, yada, 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 the y coordinate, the x coordinate, y coordinate, x coordinate. So this is the type of feedback that we can give students that are using this software, which is just really, really nice. Okay, I'm starting to run out of time. So let me do this real quick. Let me wrap things up a bit and then we'll open the floor for questions. One thing is I just need to do some shout outs and thank yous to the Math 6 and 7C faculty and staff team, Professor Jesus Lopez, Professor Jason Wang, Professor Ishen Lai, Professor Brian Rodas. Also, thank you for helping me, Brian. Professor Colleen McGraw, the math department chair, Judith Eckstein, the SMC math lab, the student coders, just a big shout out to them, Justin Chang, Jack Olson, Jason Wang, Thomas Yamada. They've just been amazing this whole time. They're still amazing. The other SMC STEM faculty who have helped, Jennifer Shia, chemistry department chair, Kyle Strohmeyer, physics department, Howard Stahl, Nathan Greenfield, both from the CSIS department, also the administrators. So we're fortunate that we have had a lot of support from our administrators, in particular, Jason Beardsley, the VP of Academic Affairs, has been on board with this since the beginning. Estella Neri, the articulation officer, has helped us craft all of the details of things. Dr. Sara Nieves Lucas, the counseling department chair, Olivia Vallejo, SMC counseling department, and then outside support. So I just want to say thank you to Mallory Newell with the RP group, Myra Snell with CAP. Thank you to Camby's Cottom, the Mount Sac math department chair, for listening to my ideas over lunch. Thank you to Lisa Morales, Paula Young, for all the support they've given the math educational community and advice they've given. And thank you to Josh at Derivata, who's also been invaluable. So now I'll open the floor up for Q&A. I suppose if you want to enter the questions in the Q&A, maybe I can answer some of them live.
Yeah, I think one of the questions was how many people were involved in developing the course, and I think you just kind of showed all the people that were involved in developing the course. Also, what kind of funding
Yes.
were you able to secure to support the project?
So on the actual development team, there's about 11 people, including faculty and students. If you want to include administrators and beyond, there's more than that. So there's a lot of people that have been helping out. Funding came from a few sources, from AB 1705 funds, some from lottery funds. Other questions?
Oh yeah, someone has their hand up. I actually don't know how to
Ooh,
Oh, I know.
here, let me do this too. I'll come back to that
Oh,
slide in the end.
someone had their
See.
hand up, but then they put it down. It went by very fast. I couldn't see it. Oh, there we go.
Oh,
Joseph,
oh,
I'm opening it so that he can speak.
Uh, it wasn't I who had my hand up, but initially. But anyway, I want to congratulate the speaker on an excellent presentation, and I'm very proud of him. He's my former student at Cal State Long Beach.
thank you, Dr. Banish.
It's a very full course, but let me just throw in a couple ideas for which there may or may not be time in such a course that's been so extremely well thought out. You were talking about limits. One interesting thing, it seems to me, would be to ask how much money would you have at the end of 1 year if you invested it $1 at 100%, compounded instantaneously. Now that would raise the question, what does it mean to compound instantaneously?
Yeah.
Which would take you to limits.
Yeah.
It's not at all obvious what the answer would be. And it comes as a great surprise, perhaps, that it'd be a finite number. And of course, that finite number is one of the fundamental constants in mathematics.
Yeah.
So that's a thought.
Thank you.
Thank you.
Other questions. Somebody said, why did you decide on having the course 4 units rather than 6 units like we were allowed under AB 1705? And frankly, we interpreted it to mean that you could only have 4 units. So we explicitly made it exactly 4 units, including the co-requisite part, just to be safe.
Also, we spoke with financial aid, and currently we have a pre-calculus course that's 5 units with a co-requisite model that's for 7 units for the students. And so, in speaking with financial aid, the director of financial aid, they specified that when a student drops a class that's 7, 8 units, that's a huge blow in the number of units that they have, and they can take them out of eligibility for financial aid or their status as a student. So that's part of that's also part of the reason why we made the
Absolutely.
unit load the way we did.
Yeah, no, he brings up a good point because a lot of times with these co-requisite courses, they're just so many units that if a student ends up dropping it, it just destroys their financial aid. And so a lot of times when students are struggling, they'll be like, oh my gosh, I'm doing like not well in this pre-calculus class, but I can't drop it because I'll lose my financial aid. So we tried to be sensitive to that and lower the unit count a little bit. That's one of the things that we arranged with counseling. Yeah. Other
Thank you.
questions? If you want, you can raise your hand, or I think we have like 2 minutes.
There was one more question about sharing your derivative course,
And
if that's something that can be shared.
Is that, if you mean, can we share the entire homework set? That I'm not sure. I would actually have to talk to Josh at Derivita about doing that. Probably wouldn't be a problem, but I have to admit it's not fully developed yet. We're about 80% of the way through. But for example, we still need to finish coding the trigonometry sections. And I think we're almost done with chapter 4, the section on exponentials and logarithms. Oh, somebody asked, how many units is your Calc 1 with support? That one I believe will end up being 7 units. Right, because it's our Calc 1 course is 5 units, and then with the additional 2 units of co-requisite support, it'll be 7 units.
and then someone asked, do you think this course as set up is possible in full face-to-face format?
Oh, that's a good question. You mean just straight lecture? I would say no. You have to account for activity time. That's actually one of the reasons why some of the activities are designed to actually deliver the content. So it's not something where students will come in and you lecture to them for, 2 hours or whatever, and then they do an activity that like reviews it. There's some of that, but there are activities that also deliver the content itself. So for example, one that I can think of right off the top of my head is, is it ellipses? I think it's ellipses. Yeah. So students will teach them the equation of a circle, a radius r centered at the origin, and then through the activity they actually derive the formula, the equation for an ellipse centered at the origin using transformations. So that's in the transformations section, chapter 2. And then from that they will again discover or deduce the equation for an ellipse not centered at the origin. So that's one of those things where the slides themselves are not complete. The activities are necessary. Yeah. We've had some requests about, maybe making it more lecture based, but if I'm being honest, I don't know if that will work very, very well. No.
Well, thank you. We are right at 5 o'clock, so I'm going to go ahead and stop the recording.